Hi everyone. In today's video, we're going to cap off our discussion on alkenes, this time just simply looking at two reactions, the Syn-Dihydroxylation reaction, as well as oxidative cleavage. It's my goal that by the end of this video, you will be able to predict the products and show stereochemical outcomes of the two reactions we've talked about, the Syn-Dihydroxylation reaction, as well as the Ozonolysis reactions. So recall from previous videos that you can actually form these anti-1,2 diols. If you take an alkene, react that with a peroxy acid, you can form an epoxide, which you can then open with water under acidic conditions to form these anti-1,2 diols. Okay, so it's anti because they're trans to each other. There's a 1,2 relationship, and there are two OH groups, so we call them diols. So what about if we wanted to form syn-1,2 diols? Well, there's actually a method for doing this. You can take the alkene, you can react that with an osmium tetroxide to form this five-membered ring called an osmate ester. Okay, so you don't need to know the mechanism of this particular reaction, but you do form this osmate ester where the two oxygens on the osmo tetroxide add to the alkene in a syn addition fashion. So you can treat this particular osmate ester with two possible different sets of reagents, either an aqueous sodium sulfite in water or a sodium bisulfite in water. And what's going to happen is a cleaving off of the osmium dioxide from that particular osmate ester and a protonation at those two oxygens to form your syn-1,2 diol. Okay, so once again, you start with your osmium tetroxide and then you react with your sodium sulfite or your sodium bisulfite in water. So a word of caution about this particular reaction, osmium tetroxide is toxic and expensive. So the first alternative to this particular reaction that we're going to learn is to add a co-oxidant that will regenerate osmium tetroxide as it is consumed during the reaction. The common co-oxidants are N-methylmorpholine N oxide, otherwise known as NMO. So it's a six-membered ring with an oxygen and nitrogen in a 1,4 position in respect to the ring. And on the nitrogen, you have an oxygen bonded to it as well as a methyl group. So its short form is NMO. Or you can use this terbutyl hydroperoxide as another co-oxidant in this particular reaction. So now you can take your osmium tetroxide and instead of using a stoichiometric amount, in other words, a 1-to-1 mole ratio of your osmium tetroxide, you can use a catalytic amount, which means you're using only a very small percentage of it, but it will keep getting regenerated by your co-oxidants, whether either NMO or your terbutyl hydroperoxide. And in this case, you're still going to get the syn-1,2 diol. Okay? So that's alternative number one. Alternative number two is instead of osmium tetroxide, you can use cold potassium permanganate under basic conditions to achieve basically the same reaction. So take this particular alkene and this time treat it with KMNO4 under basic conditions, sodium hydroxide, and then under cold temperatures, you will get that Syn-dihydroxylated product. This reaction is also believed to proceed through a similar five-membered intermediate, which gets cleaved off to form your dihydroxylated product under basic conditions. Okay, so you either use your osmium tetroxide with your sodium sulfite or sodium bisulfite as a second step in the synthesis. You can also use the catalytic osmium tetroxide with other co-oxidants like your NMO and your terbutyl hydroperoxide. And then lastly, you can use cold potassium permanganate under basic conditions, and then you would also get the same Syn-dihydroxylated product. Okay, so that's basically about four different ways to form the exact same product. Either one of them would work in your synthesis. Okay, so lastly in this video, we're going to talk about this idea of oxidative cleavage. And in fact, there are actually many reagents that would add to an alkene and cleave the CC bond, but we're only going to focus on one, which is ozone. So let's take this alkene If you react that alkene with ozone, and then you reacted that product of that first step with a dimethyl sulfide, the short form is DMS, or you react that product of the first synthetic step with zinc with water, what you're going to form is this ketone plus this ketone. Okay, so we're definitely not going to go through the mechanism of this reaction, but I want to show you some key intermediates as we move to the product of this reaction. So take your alkene and react that with ozone. The product of this step is going to be this five-membered ring where the O3 actually adds to that alkene, and you're going to get what we call an ozonide or a molozonide. This is going to actually rearrange pretty quickly to this ozonide, where one of the oxygens on the ozone is now added onto the other side of your initial alkene. And so now you essentially have this cyclic five-membered ring. That final ozonide is pretty stable, but once you react that with a mild reducing agent, such as your dimethyl sulfide or your zinc with water, you get these two ketones. So note that the ketones are formed basically by cutting off your alkene pi bond, and I've placed a dotted line on the starting material, and then you can replace that alkene with two carbonyl bonds on both sides of the vinylic group. So that's how you get these two ketones. Okay, so we're going to cap up with two examples of this reaction. So let's take the cyclohexane on the left-hand side, and we're going to react that with ozone and then with dimethyl sulfide. So what you want to find is a vinylic group, and then draw a dotted line that dissects the CC pi bond. That is where you're going to add the two carbonyls. And then you can redraw your molecule. You don't have to really change much, just draw it in the same geometry as it started with. And then instead of having the CC double bond, put two oxygens on both of those carbons to form carbonyl groups. Note that you haven't actually cut the molecule into two because that molecule is connected by a ring. Okay, let's look at this other reaction. So you have this other alkene that's reacting with an ozone and then zinc with water. Okay, so here you have two vinylic groups. So we could cut both of those vinylic groups and add carbonyl groups on there. So your first product is going to be this ketone that comes up from the left-hand side of that molecule. And here's the other product of this reaction. Okay, so that's really it for this oxidative cleavage. And that's really it for this video. So these two reactions we learned, the Syn-Dihydroxylation and Ozonolysis reaction takes advantage of the fact that you can put these oxygenated species on alkenes and form these five-membered rings that you can then cut in a variety of ways. So if you use your permanganate or your osmium tetroxide, you can form your syn-1,2-diols. If you use ozone, you can actually cut the entire alkene and form ketones and aldehydes. Okay, so thank you so much for watching this video, and I will see you in class.